So, stream processing systems have become a fundamental building block of modern large-scale software systems. This talk will tell you how to take this paradigm of stream processing and apply it to the wide area where bandwidth is unreliable and scarce. Today, if you wanted to do streaming on data that was dispersed in the wide area, like, for instance, sensors in your house, sensors in your phone, what have you, the way you would have to do it is backhaul all the data and then process it with your stream processing system of choice. The problem is that backhaul is both inefficient and inflexible. Inefficient in that you wind up backhauling a lot of data that you didn't want, and inflexible in that you would have to specify somehow in advance what are the things to collect, and it's clumsy to fix it. It would be much better if the stream processing system itself included both ends of the wide area link so that you'd have the same programming framework processing the data as moving the data across the wide area, and then you can optimize across that. And the goal of our work, JetStream, is to do exactly that, to optimize the use of your wide area link by sort of incorporating it within the streaming system. I want to just drive home this point about backhaul. Suppose you had, for instance, a content distribution network and you wanted to process the sort of incoming logs. Well, the volume of data coming in is going to vary diurnally. The bandwidth you have will not vary proportionally. It might actually be worse than I've drawn it. I've drawn bandwidth here as roughly constant. It might easily be the case that your production workload and the data you're analyzing are competing for bandwidth. And in either case, you have a certain pair of problems. One problem we might call buyer's remorse is that there's bandwidth that you paid for that you aren't using. A different problem we might call analyst's remorse, which is that there's going to be a time when you didn't have enough bandwidth for the data you wanted to analyze, and either you dropped it on the floor or your system built up its queues and got slow. But in any event, you have these paired problems. And notice that buying bandwidth is just a way of trading one problem for the other, and that if you can fix your analyst's remorse problem by paying for a lot of bandwidth, but that's quite costly. What you'd really like is to have the system adapt to the bandwidth it has and do the best it can at every point in time. Let me give just one word of background on stream processing. The model you should have in mind is that you have a distributed system where there's input data sort of scattered throughout the world. It gets processed through a network of stream processing operators at various sites, and then the data will emerge at some other site. Right? You could imagine that you have regional points of presence at which data is aggregated and summarized and then flows out to the user wherever the user is sitting. And when I say stream operators, the things I'm thinking of are things like filtering or sampling or taking quantiles, what have you. We've really built these. Our system extends this model in a bunch of ways. Our goal is to make aggregation and degradation first-class primitives in your streaming system. Right? This way you can take advantage of storage and processing at the edge. You can buffer up data locally. You can go back and query it later, or the data will be there for you. And when you have a wide area link, we will use as much of the link as we can and no more. And the result is that we maximize goodput and keep things consistent. The two technical mechanisms that we need to achieve this are data cubes and feedback control, and I will tell you about both of them. Let me give you an example to hold in your head. Suppose, as I mentioned, that you have a content distribution network and you'd like to know, how popular are all my URLs? Well, the requests are scattered throughout the world in different sites, and the naive thing to do is backhaul everything and then total it up. We're going to extend that in two ways. One thing that sometimes gives you a very large benefit is to aggregate the data locally, to do as much sort of partial computation locally as you can. In JetStream, this is unified with the storage abstraction, so we give you sort of very nice economy of mechanism there, and then fine-grained control over how much aggregation to do. Sometimes that also is not enough, and you need to just drop stuff, right? It might be that you're willing to drop the sort of low-rank URLs in order to get good bandwidth savings. Right, that if you only care about the top 10,000, you don't really need the trailing elements. And we're going to give control over that as well. I mentioned data cubes. Let me tell you why we have this strange storage thing. So the storage abstraction has to have certain properties. It needs to be the case that if you have stored data, you can update it incrementally, and that you can update it incrementally without doing any sort of wide area consistency thing. Right? You want it to be the case that local updates get written locally without forcing you to use the network. You'd like it to be the case that when you move data over the network, you can adjust the size to cope with your bandwidth. Right? The storage abstraction has to give the system enough semantics that if you had big data that was too big for your link, you could produce littler data that fit on your link. And you can do it in such a way that you can reason about the consequences. And we need it to be the case that if you have data coming in from different sites, you can merge it without any accuracy penalty. I have data over here, I have data over there. Even in the presence of this sort of degradation, I want to have a final answer that means something. And the API that is going to give it to us is what's called a data cube. A data cube is a multidimensional array with, it's multidimensional associative array, I should say, where the dimensions can be arbitrary types and the values are aggregates. And what I mean by that is, let me give you an example, actually. Suppose you have this question about counts by URL. The way you would represent this with a data cube is to have one dimension which is time and another dimension which is URL. And then you have cells, each cell holds the count for that particular time. And what makes these values not merely values but aggregates is that we have an aggregation function. If you give me 2 cells of a cube, there is a rule that tells me how to produce 1 cell of output. And it turns out that this quite simple semantics, right? All we need is a binary function, gives us a lot. That once you have that, you can do updates. You take the new value and the old value and you apply the aggregation function. You can do roll-ups, which I will define in a moment. You can merge 2 cubes by taking the elements and aggregating them pairwise, and you can summarize stuff by selectively merging entries to reduce the size. So we got a lot of semantic mileage out of quite a limited amount of user specification. Just specifying one rule, which is how do I merge values, gets us a lot. And this could be sum, as it is in this case. It could be min, it could be max. It can be the product of the 3. You could, for instance, have in one cell the count and also the maximum latency for any request in that period. I want to just define rollup for those who haven't seen it. Here's my cube. This is a rollup by time. I have merged for every URL the entries across time. I can also roll up in a different dimension and get counts at each time across all URLs. And you can do this not merely to a complete rollup, but you can do it partially. So you could roll up from the second to the minute or what have you. And this is important because this lets us unify storage and aggregation. That the model we have is that on every site you have possibly some storage, and as updates come in, they are aggregated together into that storage. And then you could have a standing query that is looking at those updates as it comes in, and every minute giving you the results over the last minute and sending that downstream. You can also go back and do a one-off query. And both of these queries, both standing and one-off, have access to this Cube API and can ask for arbitrary roll-ups of arbitrary slices of the data. So we have quite a powerful query model attached to our storage and available sort of throughout the system. And it turns out that these semantics are going to be useful for us also as we adjust the size of the output. This is what we are going to call degradation. The basic model is that you have your data, you have some data flow operators, and then there's feedback control to adjust how big the summarized data is. That if you have plenty of bandwidth, you can send data at full precision, and if you don't have enough bandwidth, even after aggregating, you can reduce the size of your data to match. And then the system will automatically tune the level of degradation to match what you have. The challenge here is that we have to cope with a wide variety of different possible degradations, and these impose constraints on us. Let me give an example. You might think, well, I had data every 5 seconds. Let me degrade it just a little bit and send data every 6 seconds. This actually doesn't work because you can't do anything with the final answer. If you had data every 5 seconds and every 6 seconds, the natural merge is data every 30 seconds. That's no good. There's another challenge, which is that if you had data every 5 seconds and then you have 2 time series at different offsets, you again have trouble merging them. You can't get a meaningful answer out. And so the system has to enforce properties for you. And the property that makes sense here is to say the time steps have to be refinements of one another so that if you take some integer multiple of the short period to get the long period, and the offsets need to be at the sort of natural boundaries. Right? You need the per minute data to start on the minute. This is the thing you need. The system needs to enforce this. And there's a design consequence here which I want you to notice, which is that when you are adjusting the precision of your data, you can't do this continuously. It's not a dimmer switch. It moves in steps. It's more like a windshield wiper, as it were. And this matters because the system framework that's going to do this feedback needs to accept that constraint. I mentioned policy. It turns out there's more than one thing you might want to do with your data. One thing you can do, as I mentioned, is coarsening. You might do something different, like just drop the low rank values, right? You might just say, I have a cutoff, and I will drop the data below that cutoff. And these are real choices. You could do either. You could do both. They make sense in different contexts. Right? In particular, coarsening doesn't always work. This is data from the Coral Content Distribution Network. This is the savings of aggregating the per domain information. And what you see is that as you go to larger and larger time buckets, you get larger and larger savings from coarsening, which is what you would like. That, if you go, note that this is a log scale, by the way, so these are quite substantial savings. This is the result by URL. And what you see is that there's no savings here, or minimal savings here, that the domains repeat and the URLs don't. And you wouldn't know in advance which of those was the case that you had, and it might change over time. This isn't some fact of nature, it's not some fact about the web, it's a fact about the Coral workload. And workloads change. And what this means is that you don't, in general, know what is the right transformation to do to preserve your bandwidth and to make optimal use of your bandwidth. And so the natural thing that you then need is some way of writing down a compound policy to say, try this first and then try that. And in general, these trade-offs are what you get in the world. That there are some degradations that give you fixed bandwidth savings and some that give you a fixed accuracy cost, but often you can't have both. That, for instance, it turns out there are global protocols that do cutoffs, that you could do not merely a local take the top 1,000 records at this site and at that site and merge them, but you can do a global protocol that is guaranteed to give you the global top K. The price is that it does, which is great because it has a fixed accuracy penalty. You know exactly what it kept and what it didn't keep. The price is you don't know in advance what the efficiency of the protocol is. It's data dependent. There are a few happy cases where you can have both. For instance, if you were doing audiovisual downsampling or histogram coarsening, if you had 1,000 bucket histogram and you have a 500 bucket histogram, you'll really know what the savings was, and that's the good case. Mostly you have to cope with, and the system has to cope with the fact that there are sort of trade-offs here. So, given that there are trade-offs, how do we impose policies on our data? How do we, as users of this system, specify things? Well, a simple natural thought that doesn't quite work is to say, pick the operator that you want to do your data degradation, put that in the streaming network. That operator then looks at a sensor somewhere in the system that tells it how much bandwidth is available and adjusts itself. Well, what happens then if we have a compound policy, right? You might very naturally have a policy that says, over time, if you don't have enough bandwidth, increase the aggregation period, go from 1 second to 5 seconds to 10 seconds, and if that doesn't work, stop raising the aggregation period and instead do sampling, right? This is a natural thing you might want to do. Preserve semantics if you can, and failing that, do something that's guaranteed to save your bandwidth. Well, this won't work here, right? This would, if you take that simple approach of just plug the operators in, you have two operators that are both trying to respond to feedback from the same sensor. The consequence is chaos, right? This isn't a stable feedback loop. So what do we do? Well, we're going to introduce what's called a controller here, right? That you have an actuator, a sensor, and now a controller. And this will arbitrate between the different approaches you could take to bound your bandwidth. And the model is that the controller will periodically read the sensor and keep itself updated on what bandwidth is available. Operators, at a time that is semantically meaningful for them, go to the controller and say, I am currently dropping half the bandwidth. Here are the possible things I could do. Which one shall I do next? And then the controller can specify it. And what's nice about this is that we now are able to accommodate the fact that operators have fixed levels. We're able to accommodate the fact that operators have to have fixed transition points, and we can do user policies of the form, first try applying this operator, and then once it's reached its limit, try this other thing, and that you can specify that explicitly, which is sort of a very great advantage here. One other thing to note is that these levels can be adjusted dynamically, that an operator is able to sort of probe its output and dynamically specify sort of what is the expected savings from a different step. So this interface gives us a lot of flexibility in the places we want it, which we thought was highly advantageous. Let me now convince you that this really works. We used the Vichy testbed, which gave us a bunch of nodes at different sites in the US and Germany. We had them all configured to backhaul data to Princeton, and the policy was drop data if there is insufficient bandwidth. So this is the sort of simplest degradation policy you could have. You could imagine that this is image downsampling or something. Here are the results without degradation. The system is able to run at 400 megabits per second using a large fraction of the sort of overall gigabit link into Princeton. We then applied bandwidth shaping on the source side using the sort of Linux kernel bandwidth shaping mechanisms. The result, as you would expect, is that bandwidth drops when we apply bandwidth shaping and then goes back up as the queues drain afterwards when we remove the bandwidth shaping. Here's what happens to latency. You'll notice that the median latency starts rising immediately when we turn on bandwidth shaping, and it rises rapidly until you have 10 minutes of delay. 10 minutes of delay is not actually good if you have a streaming system that's supposed to keep up with real-time feeds. That's a problem. Here's what happens to the 95th percentile latency. Notice that it also goes up rapidly and that it then takes an hour to recover. This says nodes are starving. That's bad. Here's the maximum latency. Again, you observe starvation. So, and it takes the system quite a long time to then recover to normal operation when there is enough bandwidth. Here's the results with degradation. I'm going to turn it on. I'm going to turn on bandwidth shipping not only once but twice to show you that there isn't a transient there. Here's the median latency. It goes up not to 10 minutes, but to about 10 seconds. The reason it goes up at all is that the congestion management policy we have is bounding queue lengths. It turns out that if you move the data through the queue half as fast, the queue gets twice as big. It's still bounded. That's OK. You could do a fancier control loop if you really wanted one. This was good enough for us. Here's the 95th percentile latency. You will observe that it, again, stays bounded. It goes up a little. It doesn't go up a lot. 15 seconds is very much better than 15 minutes. Here's the maximum latency. It's a little noisy. Nobody is starving. This is still OK. Right? This says that even in the worst case, when you have a lot of nodes competing for bandwidth, the system is more or less fair to them, which we thought was good. How easy is this thing to use? Right? You imagine that there are analysts in the world who are going to be programming this. Is this a thing which normal humans can do? We took a bunch of sample queries based on operational experience with Coral, and we coded them up. Some simple things like this requests by URL example I mentioned, you can do in 5 lines of code. We actually had an undergraduate write that. Good. Some things are more complicated. The most complicated thing here, big requests, is as follows. Compute the 95th percentile of request size over the last minute, and then backhaul all the requests that match that. Right? You could imagine that if you're an analyst, you say, this subset of the data is interesting, bring it to me, I will inspect it myself. You can do this in about 100 lines of code in a streaming degradation-y way. This is pretty good, right? This is a rather complicated thing. Our experience is this is sort of the programming level of MapReduce. It's perfectly usable by human data analysts. It does not require a PhD to program. Good. Let me now just summarize. Well, it turns out you can embed these aggregation and degradation abstractions in a streaming system and get something useful out. That you can take the sort of basic data flow notion, you can extend it with these sort of new powerful features, and everything still hangs together. You can integrate aggregation with storage, that instead of having a storage abstraction and a separate abstraction for windowing or some other aggregation, which is the way it is in today's system, you can unify that, and that really works. It turns out that degradation is complicated, and that the semantics of the problem and the semantics of the degradations you want to do impose constraints on the system. If you get the API right, this will all fall into place. There's some things we didn't address. Right? We didn't look at the question of, given some general fuzzy notion of what you want, how do you pick a degradation? That's an exciting open question. We didn't look at embedding this in a higher level language. Today, people really do program their streaming systems by wiring operators together. It would be nice to know what sort of high level language you could do that would let you both do that and also specify how to manage your local storage and specify explicitly how to adjust your data fidelity. And with that, I can take questions. Thank you.
Hi, Naveen Duchan, Microsoft Research. Enjoyed your talk. I am puzzled, curious, because when you allow the system to drop data to save bandwidth, can you quantify the impact on accuracy? Because the resulting data that you might ship might not be useful to give any meaningful answers. So,
the answer is, in general, yes, you can quantify that. Right? Exactly what it'll be will be per degradation. Right? If you did coarsening, then the semantics are quite clear. That, for instance, as you went from per second data to per minute data, you lost information about where in that minute did the result happen. That's the data precision loss that you paid, and you know that up to the level of what minute it is, the result is exact. So for that degradation, the result is very well behaved. Likewise, if you have a global top K, you know that you had exact results on the top 1,000 or the top 500 or whatever it was that you had the bandwidth to get. So the answer is, in general, yes, you can get that. Although some degradations that you might choose to do will have less friendly semantics, and that's sort of up to you as the analyst to specify what you want there.
So for example, if you had max as the query, right? So for max, you can do some windowed operator, but essentially you have to look at each and every value and be aware of what is the query that the user issued, right? So how would it work, say, for something like max?
So if you have max, the question then is max over what, right? That if you have just max, that decomposes very naturally. You can take the max at every location before the wide area link. And so in practice, you're only bandwidth constrained there if you have a whole lot of parallel maxes, right? If you want to know the max latency, for instance, for every domain that your CDN supports. And then the way you would do the degradation is not by adjusting the fidelity of the max, but by dropping some values and just saying, I won't keep the data on maximum latency on the domains that have no requests or that have minimal numbers of requests, right? That you do some structural thing about which values you keep in order to save bandwidth there.
Right, but in sense, you're also assuming that your operators are associative and commutative, so you can actually push that computation
yes,
back
that's
to the
actually,
source.
this is why we like this cube model, which is that it forces you to have operators that have those properties. And so we have built into the data model the constraint that you have this. Therefore, we're guaranteed that we can push stuff back like that.
Okay, then one final question. In the last graphs you showed, is there also an equivalent accuracy curve? Essentially, you say the bandwidth dropped this much, and the accuracy dropped this much, so I can reason about that for some windows of time, I can trust the answer from the system, but in some other windows of time, is it reasonable?
You can compute that in parallel with the data that the main computation, yes. In this particular case, the thing that we were modeling was sort of audio-visual data. Whoops, I didn't want to show that. I wanted to show this. The model that we had for this experiment was, imagine something like you're moving streams of video data. And if you downsample your MPEG video by a factor of 2, there's people who do coding who know about, at a human level, how much worse does that image look. But it might not be something as cut and dried as quantitative data. And in that case, how you want to measure the accuracy penalty is sort of complicated.
Okay, thank you.
Next.
Kurt Collefson from VMware. Just this may be obvious, but it seems like there's an issue about stability. If you have some kind of feedback loop where you're adjusting this accuracy factor, you may want to impose some sort of hysteresis or something
yes.
like that, so that you don't,
yes.
whips back and forth between
yes.
high and low
yes.
accuracy.
One of the reasons why we have this architecture with a controller to interpose between the operators and the measurement of bandwidth is so that all of that sort of stability enhancing stuff can be in the framework and not in the operators, right? The vision is users can write their own operators, they don't write their own feedback loop. We have built the feedback loop in such a way that it is experimentally verified to be stable under a wide range of conditions.
Thanks.
Thanks again.